The recording's happening now. All right, and so what I'm hoping to do right now is to go to a problem from section 4.2. I want to go to number 10, but before we do that, I do want to clarify a couple things, situations here. The definitions that we had about whether a function is continuous or not, about whether it has absolute max or mins. Notice this. If you look at this question, the first one, the first of these five says, any function that is defined and continuous on a closed interval must have an absolute min. First reaction, what do you think? If it's a closed interval, it's gotta be. You gotta have a max and you gotta have a min. So that is a definite yes, okay? The next question clarifies why they're asking. What about if it's on an open interval? Does it have an absolute max? Well, it's possible this function's increasing and it's up on the right end. It's got an open circle, so you're never gonna get there. So it's possible if it's an open interval, it does not necessarily have to have an absolute max. It's gotta be on a closed interval, there's a theorem that says you gotta have a max and gotta have a min. But on an open interval, you don't necessarily know it. Okay. So the second question, let's see, the third one. If a function is defined, differentiable, and decreasing, if it's defined on this interval, differentiable on this situation, and decreasing, there must be an absolute min. Okay. Again, the situation is, let's look at the others and verify what's going on here. If C is a critical number, then there is a local extreme value at C. Not necessarily, okay? I'm ruling things out as we're going here. Not necessarily. You can have a critical number that the derivative is undefined. The first derivative was undefined at that point, and as a result, there could be not be, it could be going to a different circumstance there than having a local extreme. So I'll talk about that in just a minute also. If the function f fails to be differentiable, then it cannot have a local extreme value at C. If it's not differentiable, if it fails to be differentiable, then you can't do it. So the idea is, what do you think? Anybody have a thought on any of these other ones? We'll check it. We got three choices here. So this one, the second one is not. What do you think about if C is a critical number, there's an extreme value? That's not true. Now these next two, talk to me about this. If a function f fails to be differentiable at C, then it cannot have a local extrema. Anybody have a thought or an example of something you've seen or anything?
If it's not differentiable and you're incapable of finding a critical value, then wouldn't it just never exist at that specific point?
Okay, so what are you thinking then? So if it's not differentiable, okay, ask the question again.
If you're incapable of differentiating it, like let's say that it doesn't exist,
okay,
then why would you try to prove that the local extreme value at that C, that value that technically doesn't exist, why would that exist?
That would be a good point, the way example you gave, okay? Let me share another one though, okay? That was that's the right thinking, so good shot. That was a good example that would go in that direction. But cannot have, that means ever. And one situation that came to mind was recently, I saw it yesterday, was if you have a cusp, okay? It comes up and it goes up to a peak. It curves up and it curves up from the left and curves up from the right. Well, if it has a cusp, then that's not differentiable at that point. But if you notice, if it's in the interval, it can have a local extrema because it could have that peak value there, could be there, it's just not differentiable. So in this case, the fact that it cannot have a local extreme is not true. You're right, it's possible that it doesn't, but it possibly can have a local extreme. So this one's not true, okay? Do you get to just what I'm saying there?
Yeah, I got you.
Okay, good. But if the function is defined, differentiable, and decreasing, and if it's defined on the intervals, closed interval, and decreasing on the closed interval, there must be an absolute min. And that's one of the fundamental theorem situation. That's got to be true. Okay? So let's run the verify. Let's check the answer on this. And the crowd jumps up and down and says, did it say yes? Yeah, okay. It looks like, I don't see the answer. There we go. I got a smiling face on my attempt, so that must be clear. Okay, I tell you what, something I wanted to do, I want to go down to question 10. Here's an example of something. I want to go back and do a couple of them in particular, but this one has a little flair to it that just an algebraic thing that you need to be able to use to manipulate in order to get the answer to the situation. So the question's saying, find the derivative and critical numbers of the function. So first find the derivative is the first part of the question. It's got f prime, that's what it's looking for. All right, so notice what we've got here. A term to the second power, x to the second power, x to the first power, derivative straightforward. We got a natural log. Formula sheet, or else if you have it in your head, we can get that. This is x to the negative 1. So what I would like to recognize is that, that I'm going to go ahead and put it over to the screen. Well, I'll tell you what, you really don't have to. I think we've got this. Okay? What's the derivative of this first term? You bring the 2 down front and you multiply it by 1/2, you get what? 1.
X.
Yes, I heard. I'm sorry, I spoke up too soon. Subtract 1 from the 2, you get x. Yes? And the derivative of minus 4x is? Go ahead and say it, someone.
Minus 4.
Yes, yes, yes. Okay, I think everybody's in harmony on that. And now, look at this one. This is a little different situation. The natural log, if you have the formula sheet somewhere, it'd be good to have out. But you got to remember that the natural log is, that's where you get the derivative of natural log is 1 over x. So the 9's out front, and you got 1 over x. So one way to write this would be, it says use fractions where appropriate. So this would be plus, I want 9 over x, right? 9 over x. 9 over x. Okay, whoops, what happened there? I want this fraction. I want 9, and then I want x in the denominator. Okay, and then now look at this last term. So what are you doing? Let's move the x up top. It makes it x to the negative 1. We've got 36 x to the negative 1. Take the derivative of that. Negative 1 comes down, makes it negative 36. Okay, let's keep going and we got to subtract 1 from the exponent. So it's x to the negative 1. That makes it x to the negative 2. That puts x squared in the denominator. Yes? So we end up with minus the fraction here. And it's going to be 36 on top and x squared on the bottom. So I need x squared on the bottom. Anybody have some success with this that I'm not familiar with here? I've got x on top.
You have to type x first.
I have to do what?
Type x and then.
Oh, and then hit it? Oh, yeah. Thank you. Okay. Does everybody see this? And look at it and be comfortable with it, because that's the general idea of the situation. But now it's saying give critical numbers, and so the second part of it is give the critical numbers. Now, one of the situations that you need to recognize is that one specific thing that they're talking about is about critical numbers. The definition of critical numbers includes that the critical number needs to be in the domain of x, okay? So one of the situations here, one of the values that it's undefined at, this f prime is undefined, is one of the situations that could determine a critical number, okay? But notice 0 is one of those answers. It's going to be a situation that's happening. But part of the situation is to come to realize that 0 is not in the domain. You cannot plug 0 into the original function because by definition, the function itself, you can't plug in 0. So x is not in the domain of the function. But what we're going to do is solve this thing in such a way that we're going to verify what the answer is. So what I want to do is I want to go to my iPad real quickly here, okay? And I'm going to come back to this. We'll finish it. But I want to go to my iPad and finish the problem. I'm going to do this over here. This is one of the things that I was talking about, that if you have an algebraic, if you've run into this before and you've got the experience with this, then you're comfortable. But if you don't, it can be a time-consuming effort that's a little bit more challenging. And the idea is this. If you multiply through by the common denominator, remember what we're doing is we got the derivative, we're going to set this thing equal to 0, okay? We're setting it equal to 0 to find the critical numbers, all right? Where is this equal to 0?
Isn't that first x value 1/2 x squared?
Say it again.
Is this the derivative or the original function?
This is the derivative.
Okay.
Yeah, this is the derivative. And because the original function was the 1/2 x squared, 1/2 x squared minus 4x plus 9 natural log, etc. Now we've got this. And we're going to set this equal to 0. And this is a matter, there's a couple of steps that if you haven't done this before, it can be a little challenging. But you need to note right now, we're going to multiply through by the common denominator and make this into a polynomial, okay? With the understanding that x cannot be in the denominator. X cannot be equal to 0. It's by the mathematics rules, you need to set aside somewhere that x cannot equal to 0. Because after I multiply through by x squared, the denominators are going to be gone. And you can possibly forget the situation that x can't be equal to 0. So I'm going to multiply through by x squared, and I still get 0 equals, when I multiply this side, I'll write the whole thing out again. And again, if you're doing this yourself, you can just do it and be clear, but I want you to see what I'm doing here, that I'm multiplying this by x squared and this by x squared with this in mind, all right? So now I've got 0 equals, distribute that, we end up with x to the third minus 4x squared. Notice the x squared is going to cancel that x, reduce it to just 9x on top. And the x squareds will cancel, I end up with minus 36. Okay? So now I've got a polynomial that is probably factorable. And this is another step. If you haven't done that before about multiplying through by that common denominator, that's a part of the deal. But now, also, if you haven't done this before, this looks like a monster. But it's really not. If you break it into some things that have something in common that you can factor out, if it's factorable nicely, it'll show up right away. This is what I mean. So what I'm going to do is I can see that the first two terms have an x, they've got an x squared common. And these two have a 9 common. All right? So if I take the x squared out of the first two and end up with, what do I have? X minus 4. And then the second part, if I factor out that 9 I saw was common, then I'll end up with x minus 4. Right now, you can tell that this factors nicely, okay? If x minus 4 and the other, what's x minus 4 right now, are not the same, then you can't do this, okay? But this pattern is showing, since x minus 4 is common, let's take it out front. What do we end up with? X minus 4 times x squared plus 9, okay? So, and if you multiply that back out, you'll see we get this original polynomial we had there, okay? So now we can calculate what are the zeros, what are the critical numbers. So the critical number in this situation right here is, all right, so x minus 4 equals 0. And you can recognize right now that this second one doesn't fly because that that x squared's got to be -9. That's got to be a complex number. So this doesn't happen. That can't be equal to 0. But add 4 to each side, and I have x equals 4. So we end up with the critical number in this problem is x equals 4. Again, if x equals 0 was one of the factors, we'd have to be mindful of that couldn't happen because it was not available in the original function that we had started with. It wasn't in the domain. So in this situation, the critical number is x equals 4. So we'll go back to the problem set and plug in a 4. Any questions on what I did there? How I did that? Okay, that was meant to be, and you guys can solve it your way. And I'm going to go back to that original screen. Let's go back to new share and go back to our problem. All right, and you can see the problem. Yes, that's correct. I'm trying to make sure you can see the problem. Okay, now you can. All right, for sure. And now the answer, check answer, and the crowd, oh, smiling face is up here. My attempt is giving me a positive feedback. Okay? Any questions on anything that I did there? Okay, there was one other thing I wanted to look at on this set. If we go back to question number 2, I've put this in student mode so the answers wouldn't be given here. I want to verify with you, though, that the logic of these situations, and they verify in here. Notice what the instructions say. It says, consider the graph on this closed interval. And it's x1 to x9. Notice they're both closed dots there at x1 and x9, x of 9. Classify each of the 9 points as absolute max, absolute min, relative max, relative min, or none, if a point is both relative and absolute. So notice that. They're reconfirming here that it can be both an absolute max and a relative max. The text, an example in the slideshow, showed something different. And I was really kind of disappointed with that. I'm sorry that, again, that fell short. But if it is both, then identify it as an absolute max. So let's go to this situation here. Is it an absolute max, absolute min, relative max, relative min? This is a none because of the fact that if it's relative, it's definitely not absolute. And if it's relative, it's got to be on the open interval. So this is a none situation. All right, now, this one up here. Anybody have anything you want to volunteer about this one? X sub 2. It's the highest point the function can get on this interval. Therefore, it's got to be an absolute max, right? This one right here. The only choices are relative max, mins, or none. And therefore, this isn't a max or a min, so it's got to be a none. This one, it's not the absolute min, but it is a min, a local min. So therefore, it is a relative min, right? And this is a none. And then we've got another none here. And okay, and then we've got another none here. And this down here is the absolute min. Where did that go? Oh, I put the relative absolute min on the top, and nobody said anything, you guys. Absolute max and absolute min. Okay, you comfortable? Oh, and this one right here, I missed, so this is a none. Everybody all right? Check answer. Smiley face. Okay, questions on that at all? The biggest point of going through and doing that is saying, if it's both relative and absolute, that is a legitimate situation. That can happen, okay? This right here would have been a relative max at x equals 1, okay? But they didn't pick that as one of the points. Questions on that? Okay, another one I want to look at, right here. Ready? Is, all right, there's another one that was a little bit complicated with the calculation, and I want to Oh, it fell on the floor there. Thank you very much. Okay, so I want to also do, I did number 10. I want to do number 13. Let's go down to 13. Okay, look at this function. It's 5x to the, it's 5 times the square root of x. All right, now, one of the situations here. This is one where find the absolute max, absolute min of the function. And the situation is, so remember, anytime you're doing absolute max and absolute min, what you're going to be checking is the critical points and the endpoints. So you check, definitely on this problem, if we check nothing else, we're going to check 1 and 25. Plug it into the original function to see if it's an original situation. But now we're going to also take the derivative of this function, okay? So in this situation, this is a possible, I'm trying to demonstrate that here's an example where in the function, it's going to turn out when you take the derivative, notice that this is x to the 1/2. Tell you what, let's go to the pad. Let's go to my iPad, okay? And I'll come back to this. So let's go to the iPad and solve this. It's 5 times the square root of x. Okay, so we've got f of x equals 5 times the square root of x. All right? So we're trying to find the absolute max and absolute min. So we got to find the critical value. So we take the derivative, set it equal to 0. So this is equal to, before I start taking the derivative, I need to convert this to a fractional exponent. All right, now we're ready to take the derivative. Okay, so we end up with the derivative of this is bring the 1/2 down front. So I'm going to multiply it. I'm going to go ahead and multiply it out. That's 5/2 x. I'm going to subtract 1. So remember now what I've got. I'm going to do this longhand. Minus 2/2. So if you haven't gotten used to this yet, notice what it's going to be. It's going to be negative 1/2. 1/2 minus 1 is negative 1/2. So we end up with 5/2 x to the negative 1/2, which is equal to 5/2 times the square root of x. Okay? So here's a situation where the derivative is undefined. Okay? The derivative is undefined. That's one of the things of a critical point, is if the derivative is undefined at x equals 0, but it's got to be in the domain. Is it in the domain of the original function? Yes, it was. So 0 worked in the original function. Notice something had to happen. X had to get in the denominator. So this fraction of 1/2, it was less than 1. So when you take the derivative, it took the radical into the denominator. And as a result, the answer could be, x could be 0 in the original function, but it can't be 0 in the derivative. But that fits the derivative, the definition of being a critical number, okay? It's a critical number because it's undefined there. The first derivative is undefined, even though it's a value that it's in the domain of the function, okay? So we've got a critical point, a critical value at x equals 0, and we have the two, this is on the interval 1 to 25 is what we have. So we've got x equals 0, x equals 1, and x equals 25. Three of these into the function and see which one's the largest and which one's the smallest. Okay, so we got the original function I've got up top there was square root, so it's 5 times the square root of 0, which is 0. And we've got f of 1, which is 5 times the square root of 1, which is 5. And then we got f of 25, which is 5 times the square root of 25, which is 5 times 5, which is 25, right? So what's the max? Boom. What's the min? Absolute max and absolute min is what it was asking for, okay? So notice that the 0 was an important part of it's part of the answer. it determined the function of it determined the absolute min of this function. And if we had left this value out where it was where f prime was undefined, we wouldn't have had that as part of our solution. Okay? And if you look at the graph of 5x, the square root of x, it's a low point. It's not a curve. It's not the bottom of a curve or anything, etc. But that's how the situation. Okay. Did everybody see that 0? So if 0 was in the interval, then it would be an appropriate part of the answer. Ha ha! Nobody said anything. But notice it's not in the interval. So x equals 0 is not one of our things to consider. So that's out. So what's the absolute max? The absolute max is 25 at x equals what? At x equals 25. And so the absolute max is at equals 25 at x equals 5, at x equals 25, excuse me. And absolute min equals 5 at x equals 1. Okay? So what I'm saying is when you went to take the derivative, the 0 showed up as a legitimate critical point, except it was not in the interval that was being considered. So 0 needed to be included. It could have been an appropriate value if it was on the interval 0 to 25, but it wasn't. I wanted to pick this problem out because I want to show you, you've got to make sure you're conscious of the interval that it's on. And even though 0 could be a critical point, it's not in the interval, therefore it's not one you're concerned with. Okay? That was a good one. Okay. Anybody think of any other questions while we've been doing this? Okay. I tell you what, one other thing I want to do is I want to move to section 4.4 before we hit the problems. I want to talk about 4.5 and 4.7. Kind of move through those briskly, but I want to do a problem from 4.4 first. And that is going to be number 3 from 4.4. So let's go back and do a new share and do 4.4, which is right here. Is that 4.4? That's 4.2. I need 4.4. So I want to go. Okay, I accidentally canceled off a minute ago something. So 4.4, I want to hit number, what did I say, number 3? Okay, this includes the first derivative test, the second derivative test. I want to make sure we go through an example of this. And it's just here, you see me go through an example of it because it was kind of chewed up yesterday. So we've got the function, and I'm going to switch over to my iPad in a second. Okay, so, and it's asking to use the specified test. It says find local extrema. So the goal of this is, what are the extrema? Is the local max, local min type situation. Same thing to the second derivative. And this one is saying, if it's an interval, it's symbolic answers, then you list the points in the form, yada, yada, the points are coordinates, local max point, local min, and then answer the question, are they effective for this given problem? All right, so what I want to do first is let's look at the initial problem and go from there. So I'm going to go to my iPad. Okay, so I've written the problem down, and I'm going to first do the first derivative test. Okay, are we there yet? Not coming yet? Okay, here we go. I'll click on it again, and we are there. Okay, so I'm calling it FDT, the first derivative test. Let's say this is the first. Make sure that's out there somewhere. First derivative test. So I've got to take the first derivative. Now, what does this graph look like? Okay, part of the situation on this is that they've made this a problem that is, it's looking like this now. X to the fourth. We've got an X to the fourth problem, which means and it's got some stuff in between. So that means it's going to look like X to the fourth looks like this on the ends, okay? And it's probably got something in between that could possibly go like this, but it ends up looking like that. So we could possibly have a few critical points here in the situation. Being that it's X squared, it might limit it, but let's take a look at this situation we've got going here, all right? So one of the things I want to verify is that we need to take the first derivative and be able to answer the question. And typically, I won't give you something like this that's got this many factors, okay? Because the fourth power means there could be several situations, but it exemplifies something I want to get across here. So we're going to need to take the first derivative here. So the first derivative, f prime equals, now this is old news for you, right? 4x to the third minus 16x, period, right? All right, so that's it. And now we can factor this. That's the first derivative. And what's common? 4 and x gives x squared minus 4. Okay? Everybody comfortable with that? Multiply it back out, make sure it's right. 4x times I get 4x third. This is 16x. Got it. Okay, so now we can factor this one more step, can't we? We got a difference of 2 squares. So what we've got here is 4x, x minus 2, and x plus 2. So look, we got 3 factors on this thing. So there's 3 places where the first derivative can be equal to 0. Does that match our graph? Yeah. We're at 0 here, here, and here. So we've got the possibility of what is x equal to? If we set this equal to 0, then we've got 4x equals 0. That means x equals 0. We've got x minus 2 equals 0, which is x equals 2. We've got x plus 2 equals 0, which is x equals minus 2. So this would be minus 2. This would be 0. And this would be 2. All right? Now the goal is to use the first derivative test. So this is going to give us some practice on this. So the idea is I need to pick a number in each of the regions in between the critical points and see what it looks like. See, does the slope change in each case? So the first derivative test, we're going to find out the situation here. Well, we got 0, -2, 0, and 2. So I'm going to pick a number that's convenient here. -3 is an integer. That'll work. A number that's easy to work with, a -1. I'm going to pick a 1, and I'm going to pick a 3. So now I need to see if the slope is increasing or decreasing at each of these values. So I've got f of -3. F prime is what we're looking at. F prime of -3, f prime of -1, f prime of 1. Probably could have left myself a little room there, but we'll squeeze it in, okay? Now look what happens here. So what I'm going to do is when I plug in -3, I've got 3 terms here. And I'm going to put down what the sign of each term is, not even worrying about what the calculation is. I could do that if you want to, but I'm just going to plug in. If I plug in -3 here, I plug -3 into 4x, I get a negative. I plug a -3 into x minus 2, I get a negative. I plug in a -3 into x plus 2, I get a negative. So that means I get a negative, negative, negative. That is a negative. Look at -1. I get plug it into 4x, I get a negative. Plug it into -2, I get a -3. That's a minus. I plug it into +2. Notice that one of them is changing at a time here. Now I've got negative times a negative, which is a positive. Look at f of 1, f prime of 1. Plug it into 4, I get a positive. Plug it into -2, I get 1 minus 2, that's a negative. Plug it into +2, I get a positive. I get 1 negative, that's a negative. Plug it into 3, I get 12. I get 1, I get 5. Okay, that's a positive. So notice by putting these in order, it allows me, I put the -3 first so I can do it in sequence here. So I have, and it matches my graph, the slope is negative to the left of -2. The slope is positive immediately to the right of -2. So that is using the first derivative test to see we got a negative on this side, a positive on this side. It's got to be a minimum. Okay? So at -2, we've got a min. All right? What about at 0? We got a positive at -1. At +1, we've got a negative. Therefore, it's positive to negative, so we got a max here. Max. This is a min. This is the first derivative test. All right? So we've got at 0, we've got a max. And then at 2, we check at 1, we had a negative slope. At 3, we've got a positive slope. Therefore, this must be a min. So at 2, we've got a min. So it's asking about local. It's saying local extrema. So, and the original question was also saying to list the point in the form coordinates. So we've got to plug, we found out the slope and stuff, and we found out the values, but we got to plug it back into the original function to find out what the coordinate is. So I've got to, so at -3, what was it? At -2, we know it's a min, but I got to figure out what the point is down here. What is this? So I got to take f of -2 is equal to -2 to the 4th minus 8 minus 2 squared minus 5, which is 4 times 4, 2 times 2 is 4, 4 times 4 is 16 positive. I've got a +4 times a -8. I got a -5. So that's -37, that's -21. So the point is, down here is going to be -2, -21. Right? Plug in 0, that's a little more straightforward. We can see right now that f of 0 is -5. So we've got the point 0 -5. Okay, and the third one, we plug in +2 is where that minimum occurred. So f of 2 is equal to 2 to the 4th minus 8, 2 to the 2nd minus 5 equals 16 minus 32 minus 5. And I got -37. I get -21 again, don't I? You can tell it's an even function kind of thing. So you get the same exact value if you plug in +2 or -2. So the other point is going to be +2, -21. So my drawing was accurate, except this dips all the way down. And down here, it's at the same height as this point is. Okay? This one down here actually is down low. So these are the 3 points. Okay, now let's use the second derivative test. All right? So I'm going to go back on the same function and take the second derivative. So I've got f the second derivative then. If I look at the first derivative, which is right here, take the second derivative, and sometimes you can do this initially right at the beginning, but that would have been right underneath it if I did it, and that means the factorization that I did would have been kind of broken up, and it might not have been as clear. I'm going to do it now. Okay, so the second derivative, I refer to this, I bring the 3 down, multiply times the 4, I get 12x squared. The derivative of -16x is -16. So what's common here? I've got -4 is common. I get +4 is common. That leaves 3x squared -2, -4, I mean. Is that right? Something's wrong with my math there? No, that looks right. That's good. Okay, so we've got to find out. Now what we can do is we can plug in the critical numbers into this function and see if the answer is positive or negative. in each case, okay? And that's going to tell us if it's concave up or concave down. So we've got our critical points are -2, so f double prime of -2, f double prime of 0, and f double prime of 2 will give us that information. F prime double prime at 2 gives us 4 times 3 times 4 minus 4, which is 4 times 12 minus 4, which is 32. 8 times 4 is 32. So that's positive, which means what? Positive means, second derivative positive means concave up. So is it local max or local min? Local min. Plug in 0, what do you get? F double prime is 0. Into the second derivative. I can plug it right into this function right here and see that I got 0 minus 16. -16. That's negative. That means it's concave down. Is that a local max or a local min? Local max. It agrees with everything. So this is a local max. Okay, and I'll say that in a second. And then at f of -2, notice what we get. If I plug it into the original function, I could have done that the first time, is I get 12 times 4 minus 16, which is 48 minus 16, which is 32, which is positive. Okay, so it's at -2, it's positive, which means it's concave up. That means a local min. So the idea was to determine whether it's a local min or a local max, and that's how you determine it. That's the second derivative test, tells you that. So, so at the point -2, -21. Okay, so if you're asked for, how do they ask it in this semester? It says in the question, it says local max points and then local min points. So the local max points, the only one that happens is at 0. So local max is at 0, -5. And local min, there's 2 of them. And the situation here, local min, and we've got 2 points here, and they're going to separate it by a comma, right? Right. So we end up with, and I'm not going to go ahead and plug those in, but the local min occurs at -2, -21, and at 2, -21. Okay? So that's for me the answer. Your numbers might be a little different, but it's the same concept. Okay, questions on that at all? Okay, so what I think I want to do right now, I'm going to move into talk about L'Hopital. Anybody have any questions that you have anything from 4.2